Namaskar. In lecture series on mechanics, I'll discuss some properties of Hamiltonian or the Hamilton's function. In my last lecture, I introduced the Hamiltonian with the help of Legendre's transformation. And I also derived the Hamilton's equations of motion. And we noticed that the Lagrange's equation, which were n in number, were the second order differential equations, while the Hamilton's equations of motion are 2n in number, but those were the first order differential equations. So it is quite easy to solve the first order differential equations. So it is one of the advantage of Hamiltonian mechanics. In this lecture, I'll describe certain properties of Hamiltonian, and before that I'll derive Hamilton's equations of motion in one another way with the help of the equation of transformation between H and L. So I may write the transformation equation or the Legendre transformation for H as, for a system of particle, H is a function of Qj, Pj in time, and this was defined as summation Qj dot Pj minus L. L was the function of Qj, derivative of Qj in time, right? Here H is the Hamiltonian and L is the Lagrangian. Naturally, H is defined in the phase space and L is defined in the configuration space. So H is a function of Qj, Pj and time. So you may write derivative of H, that is dH, as delta H delta Qj dQj delta H delta Pj dPj and delta H delta T. And if I find this total derivative of H at 1, then I get dH is equal to summation dQj dot Pj, product of two functions, dPj, then derivative of L, total derivative of L, which will be delta L delta Qj dQj delta L delta Qj dot dQj dot and then delta L delta T, right? Now summation dQj dot Pj plus summation Qj dot dPj. Now in this expression, this delta L delta Qj dQj will be written as such, while this delta L delta Qj dot is nothing but Pj, dQj dot minus delta L delta T, because delta L delta Qj dot is Pj, and naturally there should be summation symbols where J is a dummy suffix, right? Now this Pj dQj dot is cancelled and we are left with Qj dot dPj minus summation delta L delta Qj dQj minus delta L delta T, and in the left hand side you may write from 2 delta H delta Qj dQj plus delta H delta Pj dPj plus delta H delta T. So comparing the two sides, we get delta H delta Qj is equal to delta L delta Qj, and this is derivative of delta L delta Qj dot, that is delta L delta Qj dot is Pj, so it is minus Pj dot, right? Secondly, you compare this one, dPj, this one. So delta H delta Pj is Qj dot, and delta H delta T is delta L delta T. So this is again a relation between H and L, time derivatives of H and L, and this 3 and 4 are Hamilton's equations of motion. So this is another way to derive Hamilton's equations of motion. Now we come to its properties. The first property of Hamiltonian is that if Lagrangian is independent of time, Lagrangian is not depending on time explicitly, then Hamiltonian will also not depend upon time. You may see from this expression that since delta H delta T is minus delta L delta T, so if L is not depending on time, then delta L delta T is 0, and this implies delta H delta T is also 0. Partial derivative is 0 implies H does not depend on time explicitly, right? So this is one property, that if Lagrangian is independent of time, so will happen for Hamiltonian. The second property is if Lagrangian and hence Hamiltonian does not depend on time, which was the first property, the spelling is wrong, then H is conserved and it is a constant of motion. This is the next property. We know that H is defined as a function of Qj Pj dot in time, right? So what will be dH dt? It will be delta H delta Qj dQj dt, delta H delta Pj, that means derivative of H with respect to Pj dot, and then derivative of Pj dot with respect to time, plus delta H delta T, right? Now what is delta H delta Qj? You may see delta H delta Qj. Delta H delta Qj is Pj dot. It is Pj dot, and this may be written as Qj dot. What is delta H delta Pj dot? This was Qj dot. Oh, here it will not be dot. Dot नहीं है यहाँ पर. E dot. Qj dot, and this is Pj dot plus delta H delta T. So these two are cancelled and you are left with delta H delta T. Now come to this condition, if Lagrangian does not depend upon time. So if delta L delta T is 0, this implies delta H delta T is 0. So put it here. Now you get dH dt is 0. This implies H is conserved, or H is constant of motion, or H is conserved. You look at one important thing. You have defined H to be sigma Pj Qj dot minus L, right? If you remember your small h, though I'll discuss this later, but at this moment it is important to tell you that you have defined this h like Pj Qj dot minus L. Both are same, but these are same from the right hand side. But you know that this h is defined in the phase space and this small h is defined in the configuration space. This is the difference between the two. In this situation, in the configuration space, you have shown that if Lagrangian was independent of time, Lagrangian was not depending upon time explicitly, then this h was the constant of motion. And here the same condition, your L is not depending upon time, then your h is conserved and h is the constant of motion. So the same type of result is obtained for Hamiltonian, which was obtained for energy function. But up to this stage, I have not said that h is the energy function. H is the constant of motion. Now, next property is that in Hamiltonian mechanics, generalized coordinates and generalized momenta are dynamically equivalent sets of variables. What does it mean? You look at the equations. These are the two equations. This is one equation. This is one equation. And this is another equation. Delta H, delta Pj is minus Qj dot and delta H, delta Qj is equal to Pj dot. You look at these two equations. These are 2n equations. But you see, if you replace the two, if you exchange the two, you put Qj here and Pj here, you will get this equation. If you exchange the two, you will get this equation. Only the differences of minus symbol. So we come to this property that generalized coordinates, that means these Qj's, and generalized momenta are dynamically equivalent sets of variables. So this is one property about Hamiltonian mechanics. Next is Hamiltonian has the dimensions of energy, but it is not always equal to energy. First I come to this property. Hamiltonian has the dimensions of energy. How can we say this statement? You know that H is defined as H is equal to sigma Pj Qj dot minus L. H is defined in terms of L. And by the dimensional homogeneity, whatever is the dimension of L should be the dimension of this term and should be the dimension of H. L is Lagrangian and L is defined in terms of energies. It is either T minus V or T minus U. L has the dimensions of energy and therefore H will necessarily have the dimensions of energy, right? But it is not necessary that this is equal to total energy. It may or may not be equal to total energy. There are certain conditions under which H will represent the total energy, right? Now come to the next property. H is conserved. H is conserved if it is independent of time. I have proved this property earlier, that if H is independent of time, H is not depending on time explicitly, then H was a constant of motion. So H is conserved. Next is H is equal to total energy if transformation equations do not depend on time and system is conservative. If you remember, when I introduced the energy function h, small h, in the configuration space, the same type of conditions, under the same type of conditions, your small h was equal to total energy. The same is true in the phase space for Hamiltonian. Your transformation equations are not depending upon time. You have defined your h like this, right? Transformation equations are not depending upon time. That means your Ri are not a function of time. So in that case, your kinetic energy was a quadratic function in homogeneous quadratic function in Qj dot, homogeneous quadratic. So I may use the Euler theorem, which says that Qj dot delta T delta Qj dot is equal to 2T by Euler's theorem, right? And this may be written as Qj dot Pj is equal to twice T. You put it here, H is equal to twice T minus L. This is twice T minus V when your system is conservative. So it is T plus V. You get H to be equal to total energy. So if the transformation equations are not depending on time and system is conservative, then H is equal to total energy. Now if I add this condition also, that means H is also independent of time, then it will be conserved as well. So I get the result that H is equal to total energy and is conserved, right? So conserved, H is conserved and H is equal to total energy, both are different things. H may be conserved but not equal to total energy. H may be equal to total energy but may not be conserved. H may be conserved as well as it is equal to total energy. So what we get, the next property is that H may be conserved and equal to total energy. Then H and H are defined in different spaces. As I told you that this small h is defined in configuration space. So this h is depending upon, it is defined in configuration space, and capital H is defined in phase space. This is the big difference between the two functions. We come to the next property. It is in Hamiltonian mechanics, the degree of freedom is reduced by the number of cyclic coordinates, and the number of equations of motion is reduced by twice the number of cyclic coordinates. How this happens? You know that in Lagrangian mechanics, L is a function of Qj dot in time, right? Suppose your Qj is cyclic. Your Qj is cyclic or Qs is cyclic. कोई एक ले लीजिए, that Qs is cyclic. Then it is true that your Qs will not appear here, but your Qs dot will be there. So indirectly Qs is involved there in terms of the rate of change of Qs for time, or you can say the derivative in terms of derivative of Qs. L is equal to function of Q1, Q2, Qs minus 1, Qs plus 1 and Qn but q1 dot q2 dot qs minus 1 dot qs dot qs plus 1 dot qnn time, right? So all the generalized velocities still occur. So we cannot say that the degree of freedom is reduced. Degree of freedom will remain the same. But if there is some coordinate which is cyclic, then what will happen with h? Your h is defined as the function of qj, pj and time, right? Now let qs is cyclic, then delta h, delta qs will also be 0 because it will be cyclic for h as well. So what is delta h, delta qs by the definition of Hamilton's equations? Delta h, delta qs was ps dot. So this implies ps dot is 0. That is ps is equal to constant. Let it be L phi's. So you see that in this equation, in this expression of h, you are having h is equal to h q1 q2 qs minus 1 qs plus 1 qn, then p1 p2 ps minus 1 alpha s ps plus 1, then pn in time, right? And what is your another equation in terms of Hamiltonian? The another equation is, this was with minus symbol, so it doesn't matter. Further, delta h, delta ps is qs dot, right? So delta h, delta ps, what is ps? It is delta, it is alpha s, is equal to qs dot. So yeah, here differentiating h partially with respect to alpha s, you will get an expression, and from there you can get your qs, or the derivative of qs with respect to time, or the generalized velocity, the component of s component of generalized velocity. So you see that uh, your expression in this expression, one coordinate is missing from here and one coordinate is becoming constant in such a way that you can get your value like ps is equal to alpha s, and with the help of this alpha s you will get your qs dot. So in this case your degree of freedom will be reduced by 1 if your one coordinate is cyclic. Secondly, your equations of motion, your equations of motions are reduced by 2. Now I am writing that number of equations of motion is reduced by twice the number of cyclic coordinates. One equation is reduced because you are getting ps is equal to alpha s. Another equation is reduced because you may get your qs dot directly with the help of the derivative of h with respect to alpha s. So equations are reduced by 2 if number of cyclic coordinate is 1. Now we come to next property. This is the conservation theorems regarding cyclic coordinates also hold true in Hamiltonian mechanics. What are these conservation theorems? You have learnt in Lagrangian mechanics that if your translation is corresponding to a cyclic coordinate, then linear momentum will be conserved. Similarly, there was another theorem that if there is a rotation corresponding to a cyclic coordinate, then angular momentum will be conserved. The same will happen in Hamiltonian mechanics, because as in Lagrangian mechanics, we got that derivative of delta L delta Qj dot. I am writing the Lagrange-Euler equation. This is Lagrange-Euler equation, which says that ddt of this is Pj is delta L delta Qj, and Pj dot is delta L delta Qj. If Qj is cyclic, this is 0, and this implies Pj is constant or conserved, right? And we have proved that if Pj is constant, then first we prove that Pj dot is equal to Qj was representing the equation of motion. This was representing the force, and this was representing the momentum. Corresponding to the translation, it was representing the linear momentum, and this was representing the force component in the direction of translation. And in case of rotation, it was representing the rate of change of angular momentum, and this was representing the forces about the axis of rotation. And then we proved that the conservation theorems were true. That means the angular momentum was conserved for rotation corresponding to cyclic coordinate, and linear momentum was conserved corresponding to translation in the direction of cyclic coordinate. Similarly, we can prove these conservation theorems, or you can say that these conservation theorems also hold in Hamiltonian mechanics, because with the help of Hamilton's equation, delta L delta Pj is equal to Qj dot, and delta H delta Qj is equal to Pj dot. If I say that Qj is cyclic, this will be 0, and you are left with Pj dot is 0, or Pj is equal to constant. So by proceeding in the same way as I did in Lagrangian mechanics, we can show that both the conservation theorems are true for this Hamiltonian mechanics. Next is the Hamiltonian corresponding to two different coordinate systems will be different. This is a very important result. You should remember that if you have one coordinate system, which is the configuration space, you will define a Lagrangian there. Suppose your space is transformed. In the transformed space, again, if you define a Lagrangian, you may get a different type of Lagrangian. But both the Lagrangians may be different functionally, but in actual, both will provide the same real number. This is an important result. But this does not happen with Hamiltonian. You have one space, you define the Hamiltonian with the help of Lagrangian. You transform to another space, then you define the Hamiltonian. Both the Hamiltonian will be different, functionally as well as in actual value. The reason being that your Hamiltonian, which is a function of Qj, Pj dot in time, is defined with Pj, Qj dot minus L, because it is defined with the help of L, and it is not defined with the help of L directly. It is defined with the help of Legendre transformation, and Legendre transformation is involving the coordinates also. In this expression, you are involving the contribution of the coordinates also. So whenever your space will be changed, your Hamiltonian will be changed, and Hamiltonian in the two spaces will be different. So Hamiltonian corresponding to two different coordinate systems will be different, but it is not true for Lagrangian. Those may be functionally different, but in actual both will be same. So this is an important result about uh, Hamiltonian. So this is all about the properties of Hamilton's function, and now we will use these properties of Hamilton's function to analyze Hamiltonian mechanics. Thank you so much.